Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this lecture session. Today's topic is control charts for variables. This is the 19th module of the course Quality Engineering and Management. I am Subhashish Maji, professor in Mechanical Engineering from Indira Gandhi National Open University. So let us begin our discussions on control charts for variables. After listening to this video lecture, you will be able to understand the control charts for variables. You will be able to know the X bar and R charts. You will be able to explain the assignable and random causes, and you will also be able to solve some numerical on control charts for variables. The development of control charts by Shewhart enables one to control and stabilize the process at desired performance level and thus to bring the process under statistical control. The control chart consists of a central line corresponding to the desired standard of the level at which the process is to be performed and lines corresponding to the lower control limit and upper control limit. In short form, lower control limit we will say LCL, and in short form the upper control limit we will say UCL. These limits are chosen such that values falling between them can be attributed to chance variation, while values falling beyond them are attributed to lack of statistical control. Thus, points outside the limits will be signaling that something is wrong, an assignable cause. The assumptions underlying control charts is that measurement functions, that is the mean, for example, that is used to monitor the process parameter is distributed according to a normal distribution. This is evident from central limit theorem. The properties of a normal distribution hold for the sample parameter also. In particular, 99.73% of sample means fall within plus minus 3 standard deviation measured outward from the central value. These plus minus 3 sigma lines define the control limits in the control chart. In other words, the mean of a random sample of size n will lie between the limits. So, lower control limit is equal to mu minus 3 sigma by root n, and upper control limit is equal to mu plus 3 sigma by root n. The reason for adopting the 3 sigma limits as control limits is that it represents the natural variation in the process. It is clear that as sample size n increases, the UCL and LCL moves closer to center line, making the control charts more sensitive to shift in the mean. There are two types of control charts corresponding to measurements. In one, the observations are measured quantities, and in other, the count of number of defects in a sample. The former is called control charts for variables because there are variables that can be measured physically. The latter is termed control charts for attributes. In this lecture session, we shall see how the control charts for variables are used for statistical process control. Two types of quantities, that is the average quality of a process and its variability, should be controlled while dealing with measurement. To control the average quality, the means of periodic samples should be plotted on the control chart for means denoted by X bar chart. The variability is controlled by plotting the sample range on R chart or standard deviation on an S chart. The following procedures should be adopted for generating control charts for variable data. Record the measurement of K samples of size N. Typically, N is 5 and K is at least 20. So K is the number of samples and N is the sample size. Number 2. For each of the K samples, record the mean, that is Xi bar. So if there are K samples, so you will get K number of sample mean. Find the range of each sample. So Ri is the range for ith sample is equal to largest minus smallest value of each sample, where I equal to 1, 2, 3 up to K. Calculate the overall average, that is X double bar, and the average range, that is R bar, as X double bar is equal to summation of X ith bar starting from I is equal to 1 to K whole divided by K. In that way we will get the X double bar, that is mean of all means. And similarly we can calculate R bar equal to summation of all ranges for each and every samples, and this summation starts from I is equal to 1 to K whole divided by K. Calculate the lower and upper control limits, and in short form lower control limit is defined as LCL and in short form upper control limit is defined as UCL. Now for X bar, LCL is equal to X double bar minus A2 R bar. UCL is equal to X double bar plus A2 R bar. Now dear learners, there is no problem for you to calculate LCL and UCL at this stage because we have already calculated X double bar, that is equal to mean of all the means of the K samples, and we have also calculated the R bar, where R bar is the mean of all ranges for different samples, and the values of A2 are dependent on the sample size N and are given in statistical table. Plot the X bar chart with LCL, UCL, center line and subgroup means, that is X bar I. This center line has a magnitude of the overall average, that is X double bar. So X double bar is the means of individual sample. This line represents the desired average. Number 7. Calculate the lower and upper control limits LCL and UCL for R bar as LCL is equal to D3 R bar and UCL is equal to D4 R bar. The values of D3 and D4 are dependent on the sample size N and are given in the statistical table. Number 8. Plot the R chart with LCL, UCL, center line and subgroup range Ri. This center line has a magnitude of average range, that is R bar. This line represents a reliable estimate of the range. The process is said to be in statistical control if all subgroup means, that is xi bar, and ranges ri fall within the respective control limits. Finally, the process standard deviation can be estimated using sigma bar is equal to r bar by d2, and d2 is obtained from the statistical table. This is the table from which you can get the values of A2, D2, D3, D4 as per the sample size n. Now let us try to solve some interesting problems related to control limit. This is the exercise 1. Suppose we want to construct the R bar and R charts for 20 sets of diameters of a piston head. The data are collected from 3 different subgroups. The average of 3 subgroups are given 2.000, 2.0001, 2.0001 and so on. So there are 20 sets of data are given. The ranges obtained, that is the difference between highest and lowest in each sample, and these are given over here after calculating from equation 6.4 and 6.5. X double bar is equal to 2.000. This you can calculate the mean of all means. All means are given for different samples. From there, just add and divide by 20. That will give you the R double bar, that is known as the mean of bars. And corresponding to n is equal to 3, we have A2 is equal to 1.023, D2 is equal to 0, and D4 is equal to 2.575. Obviously, we have already calculated the R bar, that is the average range, that comes out to be 0.0005 for this particular problem. Hence, the R bar chart limits are obtained from equation 6.6 and 6.7 because LCL, lower control limit, is equal to X double bar minus A2 R bar. X double bar has already calculated. This value of A2 you can get from the statistical table, and R bar has already been calculated. Put the values of A2, R bar and X double bar and calculate the value of lower control limit. For this case, it comes out to be 1.99948. Now, in the similar way, you can calculate the value of UCL because the expression for the UCL is equal to X double bar plus A2 R bar. X double bar is already known, R bar is already calculated, and the value of A2 you can get from the statistical table. For this case, it is equal to 0.0005. Now, once you have calculated LCL and UCL, that gives you the control limit. The X bar chart is constructed with center line X double bar equal to 2.0000, and this is shown in figure 6.4. The R bar chart limits are obtained from equation 6.8 and 6.9. Here LCL, that is lower control limit, is defined as D3 R bar. R bar has already been calculated, but the value of D3 from the statistical table is equal to 0. So LCL is equal to 0 and UCL is equal to D4 R bar. D4 you can get from the statistical table, but for this case, for this sample size, the value of D4 is equal to 2.575 multiplied by the R bar comes out to be 0.001287. The R bar chart is constructed with center line R bar equal to 0.0005, and this is shown in figure 6.5. So this is the figure for 6.4 after drawing the X bar chart, and here you see the means of all samples are within the control limit. That means the process is under control. But dear students, in calculating, if you get the value of LCL, that is lower control limit, is negative, in that case you have to take LCL is equal to 0, because negative dimensions does not carry any meaning. The S chart is a plot of the standard deviation of a process taken at regular intervals. The standard deviation is a measure of the variability of a process. So the plot indicates whether there is any systematic change in the process variability. The sample standard deviation is a more efficient indicator of process variability, especially with larger sample sizes. The standard deviation can be calculated as S equal to under root summation of x minus xi whole square whole divided by n minus 1. X bar and S chart. The lower and upper control limits, that is LCL and UCL for X bar chart, are calculated as LCL equal to x double bar minus a 3 S bar and UCL is equal to x double bar plus a3 S bar, where S bar is equal to summation of S divided by K. The control limits for S chart are given by LCL is equal to B3 S bar and UCL is equal to B4 S bar. The values of B3 and B4 are dependent on the sample size, and we can get these values from the statistical table. This is the statistical table where we can get the values of A2, B3, B4, etc. Now let us discuss another exercise. Means of samples taken from a process for making nickel rod have a mean of 2 cm. The process variability is approximately normal and has a standard deviation of 0.1 cm. Determine control limits that will include 99.74% of sample means if the process is generating random output for these sample sizes. So we have to perform this exercise for sample size n is equal to 16 and sample size n is equal to 25. Dear learner, once you know the expression for control limits, then there is no problem for calculating the control limits for any numerical. So in this case here, that x double bar is equal to 2 cm, sigma is given as 0.1 cm and z for this case, which covers 99.74, that for that case the value of z will be 3, and this we can get from the statistical table. So upper control limit is equal to x double bar plus z sigma by root n. LCL is equal to x double bar minus z sigma by root n. So in this case n is equal to 16. So UCL is equal to 2 plus 3 multiplied by 0.1 divided by root 16, that comes out to be 2.075. Similarly, we can calculate the LCL, that is lower control limit, that is equal to 2 minus 3 multiplied by 0.1 whole divided by root 16, that comes out to be 1.925. So we have got the upper control limit that is 2.075 and lower control limit equal to 1.925. In the second case, For n is equal to 25, we can calculate upper control limit equal to 2 plus 3 multiplied by 0.1 divided by root 25, that comes out to be 2.06, and lower control limit is equal to 2 minus 3 multiplied by 0.1 divided by under root 25, that comes out to be 1.94. So you see that for two sample sizes we have calculated the control limits, that is upper control limit and lower control limit. The third problem, that is 20 samples of n is equal to 8 have been taken from a milling process. The average sample range for the 20 samples was 0.016 centimeters and the average mean was 3 centimeters. Determine the 3 sigma control limits for this process. Now in this case, x double bar is given as 3 centimeter, r bar is given as 0.016, and for n is equal to 8, the value of A2 is 0.37. So once you know x double bar, that is mean of means for the samples, r bar is known, that is 0.016. In this case, the value of A2 from the statistical table we can get, that is A2 is equal to 0.37. So all these values are known. There is no difficulty for calculating the upper control limit, that is equal to x double bar plus A2 r bar equal to 3 plus 0.37 multiplied by 0.016 equal to 3.006 centimeter, and LCL equal to x double bar minus A2 r bar, that is equal to 3 minus 0.37 multiplied by 0.016, that comes out to be 2.994 centimeter. That is the values of the control limits for these two problems. Now let us discuss another problem. 25 samples of n is equal to 10 observations have been taken from a milling process. The average sample range was 0.01 centimeter. Determine upper and lower control limit for sample ranges. For this case, R bar, that is mean of the range, is given as 0.01, n is equal to 10. From table for n is equal to 10, D4 is given as 1.78 and D3 equal to 0.22. So upper control limit for this case equal to 1.78 multiplied by 0.01, that is equal to 0.0178, that comes out to be 0.018 after chopping off the digits after decimal point. Similarly, we can calculate the LCL equal to 0.22 multiplied by 0.01, that comes out to be 0.0022 or 0.002 for this case. Let us take another numerical. A cutting operation is monitored using a mean and a range chart. 6 samples of n equal to 20 observations have been obtained and the sample means and ranges computed. So the sample 1, 2, 3, 4, 6, for these 6 samples the mean and ranges are given. For sample 1 the mean is 3.06, range is 0.42. For sample 2 the mean is 3.15, the range is 0.50. For sample 3 the mean is given as 3.11 and range is given as 0.41. For sample 4 the mean is given as 3.13 and range is given as 0.46. For sample 5, the mean is given as 3.06 and the range is given as 0.46. For sample 6, the mean is given as 3.09 and range is given as 0.45. So we have to determine upper and lower limits for mean and range charts. And the second question is the process is normal? So first of all, we have to calculate the upper control limit and the lower control limit for this particular problem. So in this case, the mean for 6 samples are given and the mean for ranges for 6 samples are also given. First of all, we have to calculate the mean of means, that is X double bar, and we have to also calculate the mean of range. So from this table, the data is given. There is no problem for us to calculate the mean of means as well as the mean of range. Now let us see how we can proceed for this problem. In this case, we have calculated the mean of means, that comes out to be 3.1. The mean of range we have calculated, that is 0.45, and the value of n is given, and for this value of n you can get the value of A2 from the statistical table. For this case, the value of A2 is equal to 0.18. So at this point, we know the mean of means, that is X bar, we know the R bar, we know the value of A2 from the statistical table, we know the expression for LCL equal to X double bar minus A2 R bar, and we know the expression for UCL, that is equal to X double bar plus A2 R bar. Just put the values of X double bar, A2 and R bar in the expression for LCL and UCL. You will get the value of LCL and UCL. For this case, LCL equal to 3.1 minus 0.18 multiplied by 0.45, that comes out to be 3.019, and UCL, that is upper control limit, equal to 3.1 plus 0.18 multiplied by 0.45 equal to 3.181. Dear learners, while performing this problem, you must see that upper control limit will be always greater than the lower control limit, because the expression for the lower control limit is equal to X double bar minus A2 R bar, and upper control limit is equal to X bar plus A2 R bar. So obviously the value of upper control limit will be higher than the value of lower control limit. But dear learners, you have to be careful for calculating LCL, because LCL sometimes, because of the values, you may get negative values. So in that case, we have to take the value 0 for LCL. So in this case, you see that partly we have got the values of control limits. Now you see that our X double bar is given as 3.1, R bar is given as 0.45, N is equal to 20. From table N is equal to 20, that value of D4 is equal to 1.59, the value of D3 is equal to 0.41. Now upper control limit for this case is equal to D4 R bar and LCL is equal to D3 R bar. So LCL equal to 0.41 multiplied by 0.45, for this case equal to 0.1845, and UCLG equal to 1.49 multiplied by 0.45 equal to 0.7155. Now you see, for this problem all the values you have got that is within the upper control limit and lower control limit. That means all the means and ranges are falling within the control limit. So the second part of the process is the process is under control? Yes, it is under control because all the means as well as the ranges are within the control limits. So the process is very much under control. Now let us summarize our discussion. Today we have discussed the control chart for variables. We have discussed the X bar and R charts. We have discussed the assignable and random causes. We have also solved some interesting numerical on control charts for variables. So in the next lecture we will take up some new topics, and by that we are finishing our today's discussions. Thank you very much.